Good heavens, did I not record that? That was such good stuff. I gotta have that recorded. Okay, I'll say it quick. Okay, I said this before, I'm gonna say it quick. Stretching out, trying to touch my toe. I've got a meter stick laying along my leg, and we're seeing how far I go on approximately 10-second intervals. These are in centimeters. The meter stick read 13,964.2. 0 is my toe. Okay. Now, if I'm pretty well stretched out, I can reach my toe, but it takes about that long. Okay. If I haven't been stretching, I've been sitting a lot and stuff, I won't reach my toe in the first try. If I repeated it, maybe I'll. Okay, so anyhow, two people got very similar observations looking at the meters. There's a little discrepancy here, a little discrepancy here, and I really don't know which one of you to trust. But trust you both. There we have it. We average the two readings. Okay, we graph this data. This is the position, which is the position of the end of my middle finger. And T is in seconds roughly. So it's counting about 10 seconds each time. So we have a graph that looks like this. It has characteristics of an exponential graph, or at least appears to. You can't tell me that this isn't exponential. Nor can you tell me that it is, because you don't know enough yet to analyze it, okay? There are things that we can do to analyze it, but I'd want more data, and I'd want really pretty specific data. I'd want to put a camera on the thing, and I'd want to repeat it several times, different legs. I've only got two, so I have to borrow some. But anyhow, there we have it. All right. Now my question is, what's the horizontal asymptote? I don't think on that stretch it would have been reasonable for me to push hard enough to get to my toe. I'm pretty sure I wanted to stop, just for safety's sake, at 2 centimeters. Okay. So I suspect that if the model is correct, the horizontal asymptote will be here. Now I've got a question mark on that. Is that my horizontal asymptote? And can I even see that on the board? Get it there, yeah. Nothing falls off. Okay, I think okay. Well, let's assume that this function is y equals a times 2 to the x plus k. Okay. I'm going to assume a horizontal asymptote, y equals 2. For this data, I'm not sure that's a good assumption. It's not far off. And that was kind of my perception. Okay, I figured I'd get to 2, and then it would be a good idea for me to stop that time. Now, if I go back and do it again right now, I'd probably get to 0 or a little on the other side. That was a cold stretch. So I'm not sure. Okay, anyhow, we're going to assume that. Okay, then what do you know about the parameters of this model? What I mean by parameters are the values of A, and I said 2 to the x because wasn't thinking as clearly as I'd like to. We're doing a lot of that this week, so watch me. Okay, a times b to the x plus k. Okay, the parameters are a, b, and k. Now, my question is, from the information we've got there and the assumptions we've made, do we have a good idea of what some of those parameters might be? Okay, now, not totally clear what the parameter k is. Let's think about it. First of all, is b going to be greater than 0 or less than 0? Tell me, is b greater than 0 or less than 0? Sorry, is b greater than 1 or less than 1? Hey, well, now I think I can trust one of you. Okay, it's all right. Well, from the first section, and go back and review it if you need to, okay? If we have a decreasing exponential, b's got to be negative, b's got to be less than 1. Think, 2 to the x looks like this, right? What's 1/2 to the x look like? It looks like 2 to the x reflected through the x-axis, or the y-axis. So, okay, so let's sketch a little picture of that. I'm going to write this as 2 to the negative x, because we know, I hope, and if you don't know it now, make sure you do by the time we get to the final. Okay, we got 2 to the x there. We do 2 to the negative x, then that flips the graph across the y-axis. Okay, means whatever x is gives you a y value. Now, if x is the negative, it's going to give you the same y value on this. Okay, so make sure you think about that. But for now, I'm going to go with that idea. And what's 2 to the x? That's 1/2 to the x. So that's b to the x with b equal 1/2. But for this thing, b is 1/2. That gives us a descending exponential. Now, since I'm writing all these words, I'm going to go ahead and color code all this. So everything in blue, or circled in blue, applies to the blue graph, which is a descending exponential. Okay, a decreasing exponential. 2 to the x, for reasons that you're very familiar with, is an increasing exponential. And the reason this decreases is every time x gets 1 bigger, you got to multiply it by 1/2. Here, every time x gets 1 unit bigger, you got to double it. We'll talk more about these characteristics. Those are all important characteristics, important ideas for understanding exponential functions. Okay. Our parameters are a, b, and k. B is a negative number. So an a, b to the x, assuming a is positive, is going to look like this. If a was negative, it'd be under. Okay. So right there's your a, b to the x. There's no k. Now what happens if k isn't 0? If k is 0, the graph is going to look like this or this. K is your vertical shift. When you shift the graph vertically, your horizontal asymptote shifts vertically. So I'm just going to make the statement. Shifted from y equals 0 to y equals 2, so k equals 2. Okay, so now y equals ab to the x plus 2. Okay. Now there are a couple of things you can do. One is to use simultaneous equations. The other is to just lower this graph 2 units and see if you can identify A or B. Probably the simpler thing to do. I love the geometric approach, and I'll explain it after I do the algebraic thing. The algebraic analysis is actually a bit simpler. Okay, so we have y equals a b to the x plus 2. Now we have two unknown parameters. Which are A and B. If we have two unknowns, and if we know 2 points on the graph, then we can get two equations that allow us to solve for those two unknowns. Now, just to put that in context, you know, if you're given 2 points and you want to find the equation with a straight line, okay? Now you have the 2-point form. It's a formula you can memorize that you can use without understanding a thing, except how to memorize a formula, and that's not bad. Okay, that's useful. On the other hand, if you got 2 points, you can sketch them. You can draw a fundamental triangle. You get the slope. And now you've only got one unknown because you know it's y equals mx plus b. Now you've done this. You remember what I'm talking about? Okay. So you got y equals mx plus b. Now you know m. What you don't know is b. But you know the 2 points. So you pick either of those points and plug them in for x and y, and you've got an equation you can solve for b. Okay? So we're going to do the same principle here, except now there are two parameters that we don't know. I'm going to say given 2 points on the graph, we're going to be able to get two equations in A and B, and we're going to solve them. Turns out, even though there's an exponential function involved, it's not difficult to solve these equations. So let's go back to our graph. let's pick 2 points on the graph, and let's not pick actual data points. Although I made the graph go through all these data points, generally, your data points are scattered a little bit about your curve. You want to get your curve that follows the trend line, that follows what you think actually happened as closely as possible. Okay, so you've got a bunch of data points. You're going to have a curve. You don't want to use any of those data points to estimate your parameters. For that reason, I'm going to go to y equals 5 here. X equals 5, sorry. Can't tell x from y. X equals 5, and we get y equals what? There's 8, there's 12, there's 10. I'm saying y is about 11. Approximately. It's an estimate. Okay, then I'm going to go over here to x equals, oh, what did I get? We don't want our points to be too close together. We want them spread out a ways because it's going to be more accurate that way for reasons I could explain, but I'm confusing you with enough stuff already, so I won't. Okay, so x equals 25. Now, what's the y value? This line, it looks like y is approximately equal to, there's 4 and there's that's about 5. Okay, so we don't want to use data points. Okay, for example, one reason we don't want to use data points is this 13 or is it 15? Okay, where is it between 13 and 15? I still don't know which one of you to trust more. Okay, so I don't know. It's between 13 and 15 somewhere. Now, if I chose to use 13, I'd get a different model than I would if I chose 15. Now, I average at 13, 15. I could use 14. That might give me a decent model. But I've got a discrepancy here too. Okay, if I use this data point and this data point, that might be a bad choice. If I use any data point, it's probably a bad choice. You probably want the smoothest curve that you can get that seems to split the difference in the data. All right. That's all worth listening to after you learn what you're doing. You won't have time to do it, but it would be worth listening to if you ever have to do this stuff. Okay, 2 data points in the curve that are not data points. We just estimated them. Estimated them in purple, so right in purple.
The only thing.
You got 5, 11, and 25, 5. Form of our model is y equals a b to the x plus 2. Okay. So plug in our XY values. Now we can't plug both of our XY values into the same equation at the same time, but we do the obvious thing, what I hope is obvious. And first we replace y by 11 and x by 5. So we get I've written out both equations except I haven't written x or y because I want to plug the numbers in. So y is 11, and b is 5. and y is 5 when b is 25. So there's our point 11, 5, 11, and 25, 5. Okay, well, we've got these two equations. Now let's think about how we might solve these two equations. Well, either you were lucky or you're smart because you nailed it, and I go with smart. Okay, that's exactly right. You don't want that 2 there. Okay, we subtract 2 from both sides, and we get now I'm writing out way too many steps, but here's our system. Here's what we do. And I really do have to write that out. For a lot of people, I know I don't have to write it out for you all often. I just need to see that. Okay, so this reduces the equation to 9. But let's just write it with our parameters on the left. AB to the 5th equals 9. And AB to the 25th equals 3. Okay. So, very good suggestion. Okay, try a couple of things. But really what it comes down to is we want to solve this equation for A. Okay. We could solve it for B, but it's a B to the 5th, and we'd have to take the 5th root, or 1/5 power. We're ultimately going to have to do that anyway, in a sense. But right now, we'll do the easier thing. It's easier to solve this for A than it is to solve it for B. So if I want to solve it for A, how do I get rid of something that's multiplied by something else in a side? I divide by that thing. Like that 3x equals 9. You would divide both sides by 3, right? And the 3 would divide the 3 and leave you with x. Okay, well, the b to the 5th divides b to the 5th and leaves you with a. Now we did it on this side, so we've got to do it on this side. Okay. And now this tells us that a equals 9 over b to the 5th. And now we take this value of a and we plug it into this equation. Plug it in here. And what equation do we get? Okay, a is now 9 divided by b to the 5th. We plug that in for a. Well, that's going to give us 9 over b to the 5th times b to the 25th equals 3. Okay, well, what's b to the 25th over b to the 5th? And let me, well, it's 9b to the 20th. Okay, if you got 25 b's written next to each other, that would be b to the 25th. Okay, and you got 5 b's in the denominator. You get 5 b's in the denominator with 5 of the b's in the numerator, leaving you 20 b's in the numerator, which is b to the 20th. It's also one of the rules of exponents. If you divide the same base, one exponent into, but set that base to the other exponent, you subtract the exponents. Anyhow, we get this. So b to the 20th equals 1/3. Now I just wrote that down, but you divide both sides by 9 And you get 1/3 over here. Okay, I don't like to write here because it's in the lots of board. Otherwise, we want to continue this. So we take this up here. So we have b to the 20th equals 1/3. Do you understand how we got that? Okay, so how are we going to solve that for b? Okay, well, I've got a really good answer there. Something about a square root, but then, well, the 20th square root, well, it's 20th root. Okay, so you could take the 20th root. It's a little easier to understand in terms of the raw rules of exponents if we take the 1/20th power. The algebra is easier to understand. There's no magic to it. It's just straightforward application of your rules of exponents. So I like to do it that way, but the 20th root is also perfectly good if you do it correctly. b to the 20th to the 1/20th then would equal 1/3 to the 1/20th. Takes the 1/20th root of both sides. Then b to the 20th raised to the 1/20th, you multiply the exponents. You raise the power to the power, you multiply the power. And this is the reason why you're sure it works. Instead of doing roots out of habit, we're just applying the laws of exponents. So make sure you know how to do it both ways. Because the explanation for why the roots work well depends on how well you know that. Okay. Again, either way is perfectly valid. Now to do 1/3 to the 1/20th, I know you can do that in your head, but don't think that hard. Go ahead and use your calculator. Okay. What is 1/3 to the 1/20th? That's the square root of 3 is that. Square root of that's going to be about that. That's 4. Go through to that. Maybe and getting like 0.94. Okay, my guess is 0.94, but I don't have a whole lot of. What'd you get? Oh, hang on. Okay, well, I come by your reaction. I kind of nailed it. The next thing maybe close to 0.95. Well, now we've got it. B is 0.94. Now, how are we going to find A? I'm going to say plug B into one of the original equations, and you can check. Now you could use this equation or this equation. Even better, you could use one of the two original equations. One of the equations still have the +2 in the end. So I'm saying plug B into one of the original equations, or better, both, in order to check. And I would use these equations. Okay. Because if you made a mistake in subtracting 2 from both sides, which I doubt you would, so it's simply going haywire here, you would you would detect that there was an error someplace. Then you would plug into these equations to see where your error came from. As a round off error, anytime you write down a value of b, so that's why it's a good idea to use both equations in this case, because you're taking pretty high powers of b. Okay, now what you do is you're plugging into these equations, and you're getting decent results. But you're using the rounded off values. Maybe it's 0.94, maybe it's 0.95, okay? I'm using 0.94, because I actually think 0.95 is a little more accurate. Fifth power 0.94, I think it's kind of close to 0.72. Do that, I think I'm within a couple of hundredths. Okay. And if you solve this, then I subtract 2 from both sides, you get 9. So you divide 9 by 0.72, you get something somewhat less than 7, maybe 6.7 or something like that. Okay. If you plug into the second equation with 0.94, what you get, I don't think that's a very good approximation. Okay. 0.94 squared ought to be about that, so 0.8 to the and that'd be pretty low. Okay, my point is, I don't think that's very accurate. I don't think that's very accurate. But you would get a very different number here than you would get here if you used a number that was only 1/100th off. Okay, and my point is, then you're going to do this using your calculator. Don't use a rounded off number. Just plug in the actual number your calculator gives you. It's going to be accurate to 10 significant figures or something like that. And then these powers ought to work out much better. There's even another strategy you could use, but I'm not going to confuse you with that right now. Okay, so despite my mental calculation here, probably went haywire, didn't hear. Now I know that A should be 7. And y'all were apparently getting something like 11.7 or something like that. When you plugged into this equation, it should have been pretty close to exactly 11. Now, how do I know that A should be 7? Okay, and don't worry about the fact that it wasn't. You know, y'all did the same thing in your calculator, using a non-rounded off value, and you came out with the same exact answer. Okay. So I'm not concerned. Those are the steps. This is how you can get data and get yourself maybe a useful exponential function. Something a little bit wrong, because we really should have come out with a number very close to 11 here when we plugged our b value in, and very close to 11 here, or 5 here when we plug this b value in. So I don't know. What could have gone wrong there? Many things, but I believe everybody understands the process quite well. Okay, what happened to my graph? I mean, this one over, thought I could see my graph. Okay, so now we have the question. Okay, now when you did 9 over b to the 5th. Oh man, I don't want to do that again. Okay, I'm gonna do it again. Okay, 7, 7, 9 over 1. Oh, wait a minute. Were you finding A or were you plugging into the equation? Let's make sure. Because you were finding.
Those were.
Okay, I did a real bonehead thing. Which is the danger doing mental arithmetic, even though I can be pretty good at it. I can do bonehead things. And I'm trying to keep too much in my head. It would be dividing 9 by 0.72. And I'm not sure what I did. I don't think I multiplied 9 by 0.72. I certainly didn't divide 9 by 0.72, because if I had, I'd have got about 12. And down here, I just subtracted this to get 3. The 3 divided by 0.17 is about 17. Okay. So I'm using 0.94 instead of 0.95 and use something I think closer to 0.95. The point I'm trying to make here is that if you use a rounded value, it's going to tend, when you get the higher powers, to screw things up. Okay, this is pretty close to what you got. You got like 11.8 or something. Okay, and that was great. We've got 17 here when we go to this power, and that wouldn't make a difference since you used the most accurate value your calculator would give you. Again, my point is, don't use rounded off values when you're doing high powers. Okay, because they really go off quickly, and that's because of the way exponential functions behave. All right. So I think we've resolved that. I don't know what I did to get people to an answer. So we've got now y equals something like 12 times 0.95 to the x plus 2. All right. My question is, how well does that model fit what actually happened when I tried to stretch? We don't have time to analyze that. About some of the numbers. There's our model. Then we would test the model against our data. Now, if you test this data model using the accurate value here and your 11.8, okay, then you can see how well the data points, how close the data points come to the, or how close the model comes to the data points, or how close the data points are to the model. So for example, let's just do one of them. Okay, one of the data points was 10, 9, right? Using your non-rounded off value of this number here, which we represent is 0.95, and your 11 point whatever, okay? Can you plug in 10 here and see how close you come to 9? We got time to do that. Go ahead. Okay, now when you plug 10 in for x using the accurate value, most accurate value calculator to give you for this thing, which is about that long, instead of 10, 9, you got 10, 9.09. Okay, so the model's very accurate at this point. I'd say it might still be fairly accurate at this point, but the one thing we want to understand is I just picked y equals 2 out of my head, not out of my head, but that's what my body was telling me would be the limit of that stretch. Okay. That doesn't mean it was a good asymptote for all this data. So I suspect if you get out here, even using the most accurate values you get, they get less and less predictive. Still, my whole hypothesis that this thing's exponential is looking fairly good right now. And I honestly don't know. I got to talk to some of our physiology people. One other comment. If we take this graph and lower it 2 units, we get AB to dx, right? If we lower it 2 units, this 14 goes down to 12. So the y-intercept is 12. So this number really should be 12. Okay. And so I don't want to get into whatever anomalies there are in the calculator internal operations. It's something a little haywire, and I want to play around with that a little bit. I don't know exactly how the arithmetic is set up, but it's binary arithmetic being applied to decimal numbers. And that can lead to little errors, so you can't always trust. Still, what you got was pretty accurate. Okay, and both your calculators gave you the same thing, and that don't look like they're the same make. Were you both using Desmos?
Mhm.
Okay, well, then I got it. Yeah. I hope I have time to look into that.